about optomechanics, and I want to say something about the general future trends in this field. So one of the things that people think about is producing some interesting quantum states, and the simplest kind of interesting quantum state would be, beyond the coherent state obviously, would be the squeezed state. So the question you can ask, squeezed state of what? The light or the mechanics? And actually you can use optomechanical systems to produce both. And squeezing of the light field is really very simple. I deal with it only briefly. The idea is that such a cavity with a movable mirror really looks like a nonlinear optical medium. So the idea is that you get an optical frequency shift that goes like the displacement, but then again the displacement is provided by the force, by the radiation pressure force. So at least in the case when you assume that there is an instantaneous reaction, the displacement goes like the circulating light intensity. So overall you have an optical frequency shift that goes like the circulating light intensity. Yeah? And this is similar to what happens, or this is completely analogous to what would happen if you had a medium with a refractive index that changes in response to the light intensity. And such a medium is called a curved medium. And now it is known that if you pass light through such a medium, this can lead to squeezing, and the idea is very simple. If you send in a light beam that has fluctuations in intensity, then you can arrange things such that, for example, if the intensity fluctuates upwards, the optical frequency shifts such that, for example, the transmission is lowered, and when the intensity is lower, then the transmission is higher. So overall there's a tendency to get rid of the intensity fluctuations. And so that leads to what is known as amplitude squeezing. Okay, so squeezing of the light field via such an optomechanical cavity is really straightforward. What I want to discuss in some more detail is squeezing of the mechanics. Now, the idea will be to exploit this optical spring effect that we talked about briefly. That is the fact that the light field can also change the spring constant of the mechanical motion. Because if you can do that, you could also change the spring constant as a function of time simply by changing the laser intensity, because the optical spring effect, just like the cooling effect, is proportional to the laser intensity. So you tune the laser intensity, and thereby you can tune the spring constant of the mechanical motion. So if I draw the mechanical potential, that would be the parabola belonging to this harmonic oscillator, I can change the curvature of the parabola in time. And now you know what happens if I place a ground state wave packet inside this parabolic potential and suddenly say I release the potential, that is, I decrease the curvature. What will happen is, in the first moment, that the wave packet will start to expand because there is less pressure, so to speak. But then the width expands and finally it contracts again. And so what you will see after suddenly switching the spring constant is the following. So let's say we plot the variance of the position, and at some point I switch the spring constant. In this case I would start expanding first and then I would start contracting, and I would get oscillations such as this. So I get breathing oscillations in the width of my wave function, and that is a squeezed state. But now maybe you are not content with the amount of squeezing you get here, and the obvious thing is to do this more than once in just the right phase, to repeat this periodically in order to increase and increase the squeezing over time. So that would be the idea. that you introduce a periodic modulation. So, in terms of the mechanical frequency, that looks like a time-dependent change in the mechanical frequency, and the easiest assumption would be to have a sinusoidal change, and if you think about it, it turns out that you need to change this frequency twice the initial or the average mechanical frequency. And so what happens then, and we will discuss this a little bit further in the following, is that if I plot again the variance as a function of time, then instead of only having once the switch and then oscillations of a finite amplitude, I get oscillations in the width of my wave packet that increase with time. So in a sense I can amplify these variations. And now indeed this has something to do with amplification, and I want to explain that now, even in the classical case. Because all of this also works if you had a completely classical, say, thermal distribution of positions and momenta, and you start changing the spring constant, then also you would observe things like this. And in classical physics, we know a very well-known everyday situation where we do change the spring constant of some device as a function of time. So I try to draw it here. So this is supposed to be a swing, and the idea is that by going up and down, you change essentially the effective length of the pendulum, because you change the center of mass here. And since you change the effective length of the pendulum, you also automatically change the frequency of the pendulum as a function of time. And you all know very well that you have to take great care of the exact phase in which you do this, otherwise you will not swing up, but you will swing down. Yeah? And we can really analyze this in some more detail now. So what I want to draw now is I want to draw a trajectory, and I also want to draw as a function of time the modulation of the frequency or the spring constant. And I will draw two different kinds of trajectories, a cosine omega t and a sine omega t, and we will find that only for one of those trajectories I will really get an amplification, whereas for the other one I will actually get a de-amplification. Okay, so here I want to draw a trajectory that is unperturbed, where I do not yet initially suppose that there is already an effect of this modulation of the spring constant. And I choose to draw a simple cosine function. Now we have to be very careful in our drawing here, because everything in the end will depend on the precise phases. Okay? So this is x of t. It's obviously a cosine. And the question is now, how should I change the spring constant if my goal is to amplify the motion? Now, in this part of the trajectory, when I'm moving back to the origin, the force also acts in the direction of motion. Yeah? the force also acts back towards the origin. It's a restoring force. So if I calculate the power, F, the force, times the velocity, this is positive. The potential feeds some energy into the motion. Okay? Whereas, of course, in this part of the motion, force and velocity act anti-parallel. The force wants to push you back to the origin, but the velocity is still going away from the origin. Yeah. So now, apparently, if I don't change the force or the spring constant over time, then the total power fed into the motion will just be zero. It's a conservative potential. I just swing back and forth, the amplitude won't change, the energy won't change. But my goal is, of course, to increase the energy. So the goal will be probably to increase the spring constant just in the moments when anyway the force acts parallel to the motion, because then the force will be so much the stronger, and so this power input will be stronger during this time interval. And to decrease the spring constant here when I would extract power. Increase spring constant here, decrease there. Here again I want to increase the spring constant because the force and the velocity are again parallel. Here I want to decrease the spring constant. So let's draw that. So here it should be large. Here it should be small, large, small, large, and so on. Okay, so if I apply this modulation of the spring constant, then I'm sure that overall force times velocity will be larger than zero, and so actually I get amplification. So the trajectory will not quite look like this, but after a cycle the amplitude will be slightly larger. Okay. And if you look at it closely, you see that the period of the modulation in the spring constant that I needed is only half the period of the original motion. So indeed I need to modulate it twice the frequency. Okay, so this was one example, but of course you could have the same modulation in the spring constant, but someone could start with a different trajectory. For example, start with a trajectory that looks like a sine function. And now look at this. Just when the force was anti-parallel to the velocity, my spring constant was maximum. So I extract energy. When the force was parallel to the velocity, because I have a restoring force and the velocity is turning back to the origin, the spring constant is minimum. So here everything is the opposite, and overall I will extract energy. So again, the same happens with the swing. Depending on where you started or what is your phase with respect to the modulation of the spring constant, you can either amplify or de-amplify the motion. And so now we can try to draw this in terms of phase space. So if I want to introduce phase space, I want to say my trajectory is x of 0 times cosine plus p of 0 divided by m omega times sine. And this is the proper initial conditions. So now initially I will simply assume that x of 0 and p of 0 might be distributed as a Gaussian, which will be the case, for example, for the thermal distribution or for the quantum ground state. And these are supposed to be the contour lines of the probability distribution. So that's at time equals 0. Now I want to look at what happened after some cycles of the oscillation. So in order to make things simple, I really take an integer number of the periods of the oscillation, otherwise I still have an artificial rotation in my phase space. Okay. So what happens then if we take into account the fact that we have this amplification and de-amplification? Well, if you look at it closely, the initial amplitude x of 0 was the amplitude as the prefactor of the cosine. Yeah? So suppose, for example, p of 0 is 0, and we have a pure cosine trajectory. We just learned that in our case, for this particular modulation of the spring constant, the cosine trajectory would be amplified. So I take x of 0, this horizontal axis, but I have to blow it up. Yeah? So the contour lines will expand, so to speak, on the x-axis. But then again, I can consider the other case where, for example, I don't have this cosine trajectory, but I start purely with a momentum initially, and x of 0 would be 0. So p of 0 is non-zero, but it is the prefactor in front of the sine trajectory. We know that is going to be de-amplified, and so I take my p of 0, but I have to multiply it with a factor of less than 1. So the contours get squeezed. And the same happens for all possible initial conditions. What I really get are these ellipses as contour lines of my new probability distribution. And so indeed, that is squeezing. I amplify in one direction and I de-amplify in the other direction. Okay. By the way, there is no possibility of having a more clever modulation or doing anything more clever in order to amplify both x and p. This is not possible because of Liouville's theorem. You know that phase space volume has to be conserved. And so if you expand in one direction, you have to contract in the other direction. And the only way to circumvent this is to introduce some other degree of freedom, because then you can say expand both x and p, but to compensate for this, some other variable x and some other momentum p will be contracted. Okay, so let's still quickly say something about the quantum version, which we already know in principle because we discussed squeezed states. Okay, so what I want to derive is simply the appropriate Hamiltonian and rotating wave approximation. So what do we have? We have an addition to the Hamiltonian, which is this part involving the modulated spring constant. So something like this. Now, if I represent x as b plus b dagger, and I take into account that delta omega squared was supposed to go like a cosine, then what I have here is this. Okay, I leave away all the prefactors here. Now we can expand this again, and I will get several terms, and the reasoning will again be that some of these terms will be unimportant. Okay, so the cosine again contains two terms, e to the plus and e to the minus 2i omega t. Let's take, for example, the term with plus I2 omega t and multiply with b squared. This, I claim, will be an important term. It's an important term because you know the equation of motion for b in the unperturbed case goes like b of t is b of 0 times e to the minus I omega t. So you already see that having the squared exactly cancels the time dependence, and so this is an important term. It's exactly in resonance. The same would go if I take e to the minus here and b dagger squared there. Plus there will be other terms, but for all the other terms you can show that they are not quite resonant terms. So in rotating wave approximation, I will only keep these two. And now I can switch to a rotating frame, a frame rotating in omega. And we already know what this means. It means that you simply get rid of these time dependencies, and my Hamiltonian in the end, if I neglect damping, will simply look like this. It will simply have b squared and b dagger squared and some prefactor. Let's call it h bar g squeezing. But this is precisely the kind of squeezing Hamiltonian that we once investigated in order to find out what is the unitary transformation that produces a squeezed state. Okay. Okay, so one question you can ask obviously is now, how would I be able to detect squeezing in the experiment? Initially it seems simple, you just measure x and p and measure it maybe repeatedly, you get the probability distribution and you plot the probability distribution in phase space and you would observe such an ellipsoid. And this would work in the classical case. Say if you have a thermal distribution and you squeeze it in this manner, then you can do this. The problem is only that if you are really in the quantum ground state here, and you try to measure x and p simultaneously, you know that Heisenberg doesn't allow them to be measured simultaneously at arbitrary precision. Yeah? And so you automatically will get a smeared version of your Wigner density, and the smeared version will be such that you don't really observe the squeezing anymore. Yeah? So you have to be a little bit more clever. On the other hand, nothing prevents you in principle from measuring individual components, say x individually or p individually with arbitrary precision. This is what we discussed. Yeah? Only if you have this displacement measurement over time, this weak continuous measurement, then you're essentially trying to measure both quadratures at the same time, and this cannot work. So the question is, can you come up with a measurement that only measures one quadrature at a time? Say only x, or only p, or only any other quadrature in the phase space plane, because if you are able to do that, then we know this quantum tomography thing about the Wigner density and can reconstruct the Wigner density. So the only question is, how do I measure a single quadrature? Say only position. Well, things would work fine if I can measure so hard that instantaneously I get the value of x. But this is really hard in these experiments. So you really want to average over time, but then again, you don't want to measure the full trajectory. And the idea is basically to have something that looks like stroboscopic measurement. So only, say, measure at time equals 0, and after some period of the oscillation, and again, after another period of the oscillation, always measure x. That will be the idea. Okay, so why is this a good idea? Well, we are dealing with a harmonic oscillator. So say I try to measure x at time equals 0. This will automatically introduce some uncertainty in the momentum, yeah? Because if I introduce a measurement of x, I will introduce some uncertainty in the momentum. So instead of the initial bare trajectory, I will get some change in the trajectory, yeah? Some random change. Now the funny thing is that for a harmonic oscillator, these change trajectories, they reconverge exactly after a full period or even after a half period. This is because of the periodicity of the motion. So that means if you only measure at integer multiples of the period, then despite the measurement changing your trajectory, at these particular points this will not really matter. It will not affect your x measurement. It would affect your x measurement somewhere in between, and it would affect your momentum measurement, but it will not affect your position measurement. So that's the idea. It's specific to the harmonic oscillator. Okay. So now how to do this in the case of optomechanical setups? Well, in principle, you know, a displacement measurement is done interferometrically. And in principle, you could send in a pulse here and another light pulse there. And then you can have a slight variation on this topic, namely you can just take the light beam and modulate its amplitude in a period commensurate with the period of the motion. So this is the large frequency of the light beam, 10 to the 15 Hertz, but then you modulate the amplitude of the light beam according to the mechanical period. And so this essentially realizes such a stroboscopic measurement. And once you really are able to detect a single quadrature, then you are able to reconstruct the Wigner density later on. And you select the kind of quadrature simply by the phase of this amplitude modulation of the light beam. If you amplitude modulate it with a phase that is shifted by pi12, then you would, instead of say x, measure p, or any other possible quadrature you can think of. Okay, so this is how people hope to be able then to measure that they do have a truly squeezed mechanical motion. Now, apart from squeezed states, what people are interested in as well are entangled states. And so you want to entangle two quantum systems, and the natural choice in this context would be to entangle the mechanical motion at the light field. And in fact, this is, at least conceptually, fairly simple to imagine. So the idea would be the following. You know that the radiation pressure force goes like the number of photons. That means if there are 0 photons inside the cavity, the mirror is not displaced. If there is 1 photon inside the cavity, it is displaced by a certain amount. If there are 2 photons inside the cavity, it will be displaced even further. Of course, I strongly exaggerate the effect of a single photon. So, never will a single photon have the effect of really displacing by more than the, say, thickness of a single mirror. Actually, you have to work hard for a single photon to even displace things by the 0-point uncertainty of motion, which is a femtometer. Okay, nevertheless, the principle is the following. If I look at my mechanical potential, which is just a parabola, then for having 1 photon instead of 0 photons, it will be displaced by a certain amount. If I have 2 photons, it will be displaced even further, and so on. So now if I were to suddenly insert a superposition of different photon numbers inside my optical cavity, then this would have the effect that also I suddenly get into a superposition of different mechanical potentials. And so in the undisplaced potential, say my mechanical ground state would still be at rest, but if the potential has been displaced by a certain amount, then what had been the ground state initially is no longer an eigenstate, and it will rather start to oscillate back and forth. Just like the same would happen classically to a particle that is first at rest, but now you suddenly displace the potential, so it starts to oscillate from here to here. And likewise, it would even start to oscillate with a larger amplitude if you displace the potential even further. Always starting from the initial position. Okay. So how do we describe this quantum mechanically? How do I write down the state? Well, I suppose I have my distribution of photon numbers, so there's a sum over all possible photon numbers, and Cn are supposed to be the amplitudes. That depends on my preparation of the photon state. So Cn multiplies the number of photons, and the number of photons, if you don't take into account photon decay out of the cavity, is simply a constant of the motion. It's fixed. Whichever number you have, it is fixed. But then for a given photon number, I have the mechanical dynamics going on. So either I remain in the ground state or I get a coherent state oscillating back and forth at an amplitude that also depends on the photon number. So I don't want to calculate the details, but I simply know that if I take a ground state and displace the harmonic potential, then what I get is a coherent state that oscillates back and forth. So I will write down the coherent state in our common notation. We'll introduce a complex amplitude. I call it beta because my phonon operators were called E. It depends on the number of photons. For example, the amplitude depends on the number of photons, and it's time dependent because it swings back and forth. And then in addition, there might be some phase. Okay. So this is the full state of the system, light and mechanics, after some time t. And you see that it is an entangled state in the sense I can no longer write it as a product state. I cannot write sum over photon numbers times some state of the mechanics that is completely independent of the light field. They become correlated. So this is already interesting. How could you observe this in principle? Well, there was an idea put forward by Jack Baumeister and Roger Penrose. They imagined you would have an interferometer, say a Michelson-Morley interferometer. And this interferometer is supposed to have 2 cavities, one in each arm of the interferometer. But one of those cavities is supposed to have a movable mirror, like this one. So now what happens is the following. You first insert a photon at a given time. It may enter this path where it simply bounces back and forth and then exits. This is, so to speak, standard. Or it may enter this path, and when it does so, it gives a kick to the mirror. Now the problem is that if the 2 paths recombine later on, then if the photon really has left a trace in the mirror motion, that it had been here instead of there, then you have something like a which-way experiment where you have detected the fact that the photon is here instead of there. So then we learn that the interference will get lost. So if you look at an interference pattern here, say by changing the phases in the different arms, you won't see any contrast of the interference pattern anymore if your photon really has left behind a trace inside the mechanics. So now we can, say, draw the contrast of this interference pattern as a function of time. And so what you expect is that photons that exit very quickly did not have sufficient time to interact with the mirror and to make it swing. And in this first instant, then the contrast still is 1. Yeah. But then very quickly, the photon has some time to create this entangled state. If there is entanglement between the photon and the mirror, then automatically the interference will get lost. This is the kind of decoherence which we discussed. So you quickly go down here. And how quickly this happens depends on all the details of the parameters. But interestingly, this is not the end of the story. Actually, if you were to make this experiment, then after some time, you would recover the contrast. And again, after some time, you recover some part of the contrast. So it turns out this time is exactly the mechanical period. And why is that? Why would you recover the contrast after exactly the mechanical period? Well, this can be explained by the picture with the potentials that we have here. So what happens is the following. At first you displace your potentials, then the mechanics starts to move, would swing forward and backward. But after a full period it has exactly recovered the initial position. It will sit here, exactly like if there were no photon. And again, even in the 2-photon potential, it has gone forth and back and exactly returned to the origin. Yeah. So after a full period, you exactly return to the initial state, and it is as if there were no photon. So after a full period, actually, all these coherent states conspire to be the same as the initial state. And so you can factorize them off, and it is no longer an entangled state. The light and the mechanics again factorize. And because of that, the light is practically independent of the mechanics, and you regain the interference. So that is why you can regain the interference contrast. And this happens periodically. Okay. So here I already draw the more realistic situation where you don't recover the contrast completely. And that is because during this time, what can happen is, for example, that your mechanics couples to the environment, for example, to the substrate. It emits some phonons into the substrate with a certain probability. Then some of the information gets lost, it gets dissipated in the substrate, and it will not come back. Therefore, it's not possible to fully come back to the initial state, and therefore you still retain some entanglement. So instead of being entangled with the mechanics, it's actually entangled with the mechanical bath, for example, the substrate to which the cantilever is attached. But in terms of interference contrast, this doesn't matter. You have left some trace, so instead of having a swinging cantilever, you now have a phonon traveling in the substrate, but this is just as good. You have left a trace that the photon has been in this arm instead of the other arm of the interferometer. And so you don't recover the contrast completely. Okay, so anyway, this is a very nice experiment in principle to prove that there is entanglement between light and mechanics, and also by way of these revivals to prove that it is really the mechanics, because this is the mechanical period. If you had lost your coherence because of other sources of noise, you would not recover it. Okay. Still, nevertheless, there is this extra decay because of decoherence of the mechanical motion, and so people came up with the idea that this might serve as a tool to investigate decoherence of these mirrors. And in principle that's true. And they even came up with a rather crazy idea that this might be used to investigate decoherence of extra unknown, as yet unknown decoherence sources, so to speak. And I want to explain the example that people have become excited about. Okay, so the idea is, can we test for extra decoherence sources? And the question is, of course, why would you use these optomechanical setups if you could as well, say, look into light or spins or single electrons in a semiconductor and so on to study decoherence? And the answer here is that these mechanical objects would be very massive. They carry a large mass as compared to all the single atoms and single electrons and so on. So if you can come up with a source of decoherence that depends on the mass, essentially, then it might be true that these systems are particularly good for studying that. And if you think of mass, well, people thought of gravity. So I'm now recounting speculation or hypothesis by Roger Penrose. The idea is that gravitation might induce extra decoherence of quantum mechanical objects, and this could be visible if the objects are heavy enough. So the idea is you have an object that carries a certain mass, and you somehow manage to bring it into a superposition of being in two places. And so these could have a distance d, and even quite generally for any arbitrary sources of decoherence, you assume that the rate at which decoherence happens increases when you increase the distance between the two locations of your superposition. That is reasonable, yeah? Decoherence becomes stronger if the distance becomes larger, because the superposition then is larger. Now, if you want to speculate about gravitationally induced decoherence, then the question is, can you come up with some formula for the decoherence rate or the inverse decoherence time? Independence on, say, the distance, and also independence on the mass. And so if gravity is to play a role, you don't really have much choice in terms of dimensional analysis. There are not so many parameters around. Probably you would want to have the gravitational constant appearing. And so the idea very roughly is the following. If you only have one mass and one distance, you can construct a gravitational energy that looks something like this. And so if you have an energy, if you give me any energy and allow me to use Planck's constant, I can construct a frequency. And that would be a frequency. So the idea is then to have something like 1 over h bar times a gravitational energy. But I want to set up things such that if d goes to 0, I automatically get 0 decoherence rate, because then there should not be any decoherence if there is not really a big superposition. So what the proposal was the following: to take the mass density, but not really the individual mass density, but rather the difference of mass densities, because this somehow counts whether there's a big superposition, whereas if the objects are really sitting at the same point, then the difference of mass densities will simply be 0. So I call this rho left minus rho right. So this would go to 0 if the distance goes to 0. And then calculate simply the gravitational energy belonging to this mass density, delta rho. So you integrate over r and r prime, delta rho of r, delta rho of r prime, divided by r minus r prime, and you multiply by the gravitational constant. And so the speculation is that there might be some extra decoherence rate that somehow looks like this. And if you want to plot it as a function, say, of the distance, then what happens? Well, at large distances, the term, the cross term that connects rho left to rho right, basically vanishes because 1 over d vanishes. All that remains is the gravitational self-interaction, that is rho left squared divided by the radius of the object, so to speak. So you get a constant at large distances. At small distances, delta rho becomes 0, so you get 0. If you're not at very large distances, then you find a first correction that goes like 1 over d. And then you interpolate smoothly, and you have a curved part that is determined by the actual size of the object. So the decoherence rate would look somehow like this, and it is not completely unreasonable. There are other instances of other decoherence mechanisms where the dependence of the decoherence rate on distance does look similar. Okay. Now the question is, why don't we have observed it so far? And that you can answer by doing an estimate. So, for example, if you have a mass of 1 nanogram, which for microscopic objects is already fairly heavy, and a radius, say, of 10 micron of your object, then you can calculate at least what is the maximum decoherence rate out here. That is due to the gravitational self-energy. And you find that the corresponding decoherence time thus is larger than, say, 100 microseconds. But this would only be the correct decoherence time if you really were to displace these two positions by more than the radius, if you're somewhere here or there. And of course it's completely impossible to display so far to produce superpositions of objects weighing 1 nanogram, that is about the size of these mirrors, by 10 micron. You can be happy if you are able to displace them, say, by a picometer or even a femtometer, and produce a coherent superposition initially in order then to test this decoherence mechanism. So that's why it's really hard, because the point is, if you go down here in distance, then the decoherence rate goes down, so the decoherence time goes up. And by the time that the gravitationally induced decoherence mechanism would become important, maybe you have already lost the coherence completely because of all the standard decoherence mechanisms. So that's why it's difficult. But it also shows that it's important to have this comparatively large mass. If you were to go to microscopic objects, then the mass would be smaller by many orders of magnitude, and here you have the mass squared entering, so you get a really tiny decoherence rate, and you would never be able to observe it anymore. Okay, so how realistic is this, apart from the question of how to observe it? How realistic is it that there might be such a decoherence process? Well, the point that people make in favor of this is simply that we don't yet have any complete theory of quantum gravity, so we might as well speculate that it is somehow different. But what we know for sure is that, for example, in quantum electrodynamics, there is no such thing. In quantum electrodynamics, you could also say I have a charge that is in a superposition of being here and there, and so it has different electric fields depending on whether it is here or there. But there the answer is simply that yes, there's an entangled state entangling the position of the particle with the structure of the electromagnetic field. So either you have the particle here and the electromagnetic field lines around here, or the particle is there and the electromagnetic field lines are around there. And there's no problem in that, and there's no decoherence associated with that. So if there is really such a decoherence mechanism, then it would have to be really very different. Then quantum gravity would have to be very different, say, from quantum electrodynamics. And now, then it depends on whom you ask, but for example, if you ask our dear loop quantum gravity colleagues, then the way I understand them, one essentially applies more or less standard quantum mechanics to gravity in their case, and therefore one would expect to see phenomena similar to quantum electrodynamics, and so one would not expect, from their point of view, this decoherence process. But maybe we have to check. Okay, so much about fundamental quantum mechanics. The last item I want to mention is something relatively new in terms of the structures that can be fabricated, and that is called optomechanical crystals. That was introduced last year by the group of Oscar Painter at Caltech. Now, what do these structures look like? The idea is to miniaturize everything and use the tools of nanofabrication. What do these structures look like? Well, one of the typical structures would be having a beam, like the ones where you would produce a tiny mirror on top of it, but instead you simply pattern the beam, that is, you have a lot of little holes inside the beam. Okay. And now what's the purpose of this? Well, if this beam is simply made of some dielectric, then obviously, in this case, it is a patterned dielectric. And so what you find is that light propagation in periodically modulated in a patterned dielectric is simply like electron propagation inside a crystal lattice. So just like for the crystal lattice, you will find bands. You will find bands for the light field, and in particular you can also find band gaps where the light field is not allowed to propagate. And these structures are typically called photonic crystals. Now, photonic crystals have been known for some time and are very interesting by themselves, but here an additional feature was added, namely it's a beam, so it's freestanding. It's freestanding and it can vibrate. Okay, so we have light and we have mechanics, that is already good, but what we really want to have is something like an optical cavity. And now the idea is that it is very easy to produce something like an optical cavity or a localized optical mode in such a photonic crystal. And the idea is simply the following. You take these holes and you somehow change, say, their shape as a function of coordinate. And that produces what you could call an artificial defect. But now it turns out that if you produce this in the right manner, this artificial defect will automatically lead to a localized optical mode, or actually to many localized optical modes. And since the structures we are talking about are in the range of a wavelength, this micrometer, also these localized optical modes are only very few micrometers. So compared to the typical optical cavities you have, they are really tiny. They are as tiny as they can be because that's the wavelength of light. Now, the funny thing is that not only do you have a localized optical mode, but also mechanical propagation of sound waves is modulated by this periodic structure. And it turns out that right at this artificial defect you also get localized vibrational modes. And then the idea is that they start to interact, because you can basically do anything you like. If you get a displacement of this localized vibrational mode, then you distort the structure, and so almost always, except for certain cases dictated by symmetry, almost always this change in the structure will automatically also change the optical frequency. And that is exactly what we want to have for an optomechanical system. You want to have a displacement changing the optical frequency. So why are these structures so good? Well, first of all, with regard to the localized vibrational modes, they are very tiny. I mean, they are as tiny as they can be, on the order of a few micron, and so they have a very lightweight mass, and these structures can be made very stiff, so the frequencies will be very high. And high here means on the order of gigahertz. And so this is very promising, because if you have gigahertz mechanical vibrations, then you can calculate for yourself that even say at 50 millikelvin, which can be reached in typical dilution refrigerators, you might go already into the ground state. So maybe you can get even rid of this extra optomechanical cooling. You just have your refrigerator, you have this mode, and it's automatically cooled. Another effect is that since both the optical and the vibrational mode are so localized, they have a very strong interaction. You remember that in our case the optical frequency shift per displacement went like the optical frequency times x over L. L was the length of the cavity. Now here the length of the cavity is only micron instead of centimeter, so this automatically provides a very large coupling. And in fact, if you calculate the optical frequency shift per displacement, then you get numbers on the order of 100 gigahertz per nanometer, and that is really orders of magnitude better than what was possible previously. And now if you have these very nice optomechanical cells, what can you do with them? Well, one of the points is if they are so small and if they have been nanofabricated on the surface of a chip anyway, you can have more than one component. You can integrate many of these components and build some circuits. And in these circuits you can combine many functionalities. For example, you could do sensing, like displacement, force or mass sensing, and then you could use the signal and amplify it, either a light signal or a mechanical signal, in one of the ways we discussed, and then you could do further signal processing, and you can even store the information and send the information elsewhere by the light. And also on the more fundamental side, you can say, if it's so easy to produce a localized optical mode interacting with a localized vibrational mode, I can as well have many of them on the same beam, for example, and that will allow me to study their interaction. So I have many of these optomechanical cells, and I can study their collective dynamics. And that could mean either classical collective dynamics or quantum dynamics. So what we are looking into right now would be the classical collective dynamics, And one of the most interesting cases is where you excite these self-induced oscillations. You remember there's the cooling side of the resonance and there's the heating side of the resonance, where you can go into self-induced mechanical oscillations. And now if you have oscillations in each of those cells and they interact with each other, then they can, for example, synchronize their oscillation. And that might be better for some applications where you really want to have very stable frequencies, and then if you have many oscillators and synchronize them, that's better for stability. Okay, so that would be collective dynamics of these objects, and then you can also ask about collective quantum dynamics. So you have cells which contain both photons and phonons. They interact with each other, they become a nonlinear quantum system, so to speak, a quantum many-body system. It's also driven at the same time, and it is dissipative. And so it's very interesting to try to figure out what happens in such a system. Okay, I think that's enough for today. Are there any questions? Well, if not, see you next time.